my last lecture, and today we're going back from maps to graphs, where we started from on the first day. If you remember, on the first day we studied the layout algorithms for planar graphs and how to draw them on a nice grid and having small area. Today I want to talk a little bit about if your graphs that you want to draw are not planar, yes, and what you do. Not all graphs are of this kind of nice type that you can draw them in the plane. You get faces, face structure, topology. You don't have any crossings, so you can kind of do it nicely. We know that this only works for graphs that have at most 3 n minus 6 edges, say. Or they have no k5 as a minor or k33. So, of course, if you go to real-world data, then very frequently what you see is networks like that. If you use a standard algorithm, using, for example, four-space layout, then visualization researchers call this kind of graph a hairball graph, and you know why. Yeah? So there's just the graphs are so dense, have so many edges, that there's no hope of doing it in a crossing-free way, and then it's even challenging of distributing the vertices in such a way that you can at least see, if you take very carefully maybe a ruler, which two vertices are connected. I mean, here it's on the outskirts, maybe you see some connections, but in the inside it's just almost a clique, but you never know whether two nodes are connected or not. So in this lecture today we will see a little bit of techniques, but maybe more motivated from algorithms and theory, how to deal with crossings if we know that they cannot be avoided. Okay, so and this lecture has two parts. In the first part I will maybe give an overview of different techniques that have been developed, or different layout styles for displaying edge crossings, or maybe even not displaying them, so kind of cheating to have them invisible in some sense. So the first part will be on a very, very high level in some sense, so I will give an overview of some results that are out there, but not go into details of proofs or algorithms. And then in the second part we'll see some algorithm for non-planar graphs. So this part will cover 5 topics, and the first 3 you can say they are kind of ideas of making, if you cannot avoid the crossings, then at least try to make them somewhat nicer in the sense that readability is not so bad in the graph. And the second part will be about eliminating the crossings so that you don't see them anymore in the layout. We will see what that means. Yeah? So if, for example, if you have this graph here, this is K5, and it doesn't look so bad, even though it has lots of crossings. So the question is, what can we do to have graph layouts that are still kind of readable, even though they are non-planar? So the first layout style is so-called slanted or smooth orthogonal drawings. And you also remember from, I think, the second lecture where we talked about schematic layout of graphs and orthogonal layouts, that we have seen many graph layouts that are almost like that one. Oh, let me get my laser pointer. So if you forget about these small, short diagonals, then these look almost like orthogonal drawings. And what the slanted orthogonal drawings do is that they additionally allow use of some diagonal edges, like we did in the metro maps. They use them to make sure that every bend is kind of 135 degrees. Yeah, so there's no very sharp bends. And one extra property is that if you need two edges that cross, they always cross only on diagonal segments. Okay, and if you imagine you have a very large graph in that style, having the crossings on diagonals and the nodes using horizontal and vertical edges is a good idea of distinguishing between what is a crossing and what is a vertex. Yeah, because if you look far away, you could think maybe there's a degree 4 vertex here, but the style of using diagonals makes clear that this is not a vertex. Yeah, so this is so-called slanted orthogonal drawing. We will see a little bit more. And the smooth orthogonal drawing uses now, instead of straight line segments, uses pieces of circular arcs for drawing the edges. And I mean, all the drawings that you see here is K5, right? So this was the very symmetric classical one. This is one with a single crossing at 90-degree angles and using diagonal edge segments. This is a similar one, but now we use circular arcs. You can see there's some quarter circles here, some semicircles, and we can do this in a polyarc way, so composing like a semicircle from here to here and then a straight line segment, but making sure that all the tangents meet nicely so it has a smooth appearance. The next technique is called edge casing, and it's an idea of making sure that this has somewhat a 3D appearance, or at least 2D plus a little bit, in the sense that you can, by interrupting one of the two edges of a crossing, create the appearance that one of the edges is above the other one. So you can think of this being a bridge and this being an underpass of that crossing. And in that sense, somehow it might look a bit nicer. This is the edge casing technique. Then people also studied bundled crossings with the idea that you can group or maybe multiple crossings between the same two subsets of edges into small regions like pseudo-circles where all of those crossings are bundled. So this graph actually has 5 crossings, but if you just count bundled crossings, it has 3 crossings. Okay? And by doing that, in some sense, you create the appearance that there's fewer crossings than there actually are, by grouping them. Sometimes this might be useful in applications. And the second part is about eliminating crossings in the sense that you show the graph in a style that you don't see the crossings anymore. Okay, we cannot do magic tricks here. If it's a non-planar graph, we cannot embed it in the plane without crossings. But what this Confluent style does is that you indicate adjacency between vertices by the existence of a smooth path in that system of arcs. Okay, so think of this like a toy train that you have on your train tracks. And if you can move the train from one station to the next without going forward and backward, then this would indicate that there's a connection. So in this particular layout, you have all-to-all connections, like a roundabout, and that means it's K5. Yeah? But without crossings. I mean, the crossings are somewhat there because you're sharing segments here, but it doesn't look like that. And the last one, you can say it's cheating, but it works kind of well for humans because of Gestalt theory. So in psychology, you know that if you see something like that, it might still, I mean, depending on what your brain does for you, but it might still look like the standard K5 drawing, even though we interrupted some of the edges. So maybe you see the little star in the middle, or at least you can connect these two stubs into a single edge. And then you see the full connectivity of that graph without seeing the crossings. Okay, that's also a trick, and then you can try to optimize different things in these kind of layouts. So it's kind of non-standard layout styles that we see here. Okay, let's start with making the crossings nicer. And we'll start here with the orthogonal style layouts. So this is a standard orthogonal layout of K5 here with a single crossing. And the idea of slanted is, I kind of quickly sketched it on the previous slide, but we want to have a slanted orthogonal drawing where edges enter the vertices only using the 4 main ports, north, east, south, and west, like you see here. Then every edge is represented as a polyline using horizontal, diagonal, and vertical line segments, but any 2 consecutive segments must have a large angle of 135 degrees. And only the diagonal segments may cross. So this is the definition of slanted orthogonal layout. Yes, that was the highlighting. And you see here the difference. And if you're sitting in the back, maybe this might appear like a vertex if you're far away. Using the diagonals, it's kind of better. And then for smooth orthogonal drawings, you can again use only the 4 ports for each vertex. Now we have sequences of circular arc of line segments, and we must make sure that if 2 arcs meet, then they have the same tangent. So if you study these types of drawings, you might wonder what is maybe a measure to optimize or to minimize here for the quality. And one thing that you can do is to count the kind of complexity of the drawing in terms of the number of line segments that you need to draw all the edges. Okay? If you go here and start counting all the segments, so for example this edge here consists of 4 segments, okay? 2 vertical and 2 horizontal. And if you do the counting, you see that this layout has 22 segments. If you go to slanted, because now you need to create from a 90-degree angle, basically you take the diagonals to cut it off and make it more smooth. Of course, you increase the number of segments. Question is, what is the trade-off? Does that look nicer or that one? Yeah, that's up to maybe user studies to see readability. But if you go for smooth orthogonal, you can again lower the number of segments, because like a 90-degree turn or even 2 90-degree turns in sequence can be represented by a single arc. Yeah, so here you would have 15 segments. And maybe one interesting question is, if we allow to make that edge slightly larger radius, then you save 1 segment, but you increase the drawing area. So there's these kind of trade-offs that you typically find in graph drawing. Yeah. Okay, so what is known about these slanted orthogonal drawings, or sometimes called SLOC drawings for short? So you can compute, again, bend optimal slanted orthogonal representations using a very similar network flow mechanism like the one that we've seen for bend minimization in orthogonal layouts. Yeah, if you remember that, we had vertices for faces and vertices in the network for the original graph nodes, and then computed a minimum cost flow that gave us a number of bends here. You can do a very similar thing if you have such a slanted orthogonal representation. If you are given a SLOC representation like that one, then if you remember the framework, the next step was to get metrics and compute the length of the different edges. You can compute actually a close to bend optimal, but not fully bend optimal layout, at least on a quadratic size grid. So area is kind of nice, but maybe you use slightly more bends than necessary. What the authors here also presented in their paper is an Ilp model. So we've seen also integer programming as a technique for metro maps. And with that technique, they can compute bend optimal drawings, so really getting the optimum for a given representation. But it's unknown whether this ILP always has a feasible solution. So there's kind of a problem in the model. Yeah? So it could be that for some cases it doesn't give a solution. But I think some of the layouts that you see down here, they are taken from their paper, have been computed with this ILP approach. Yes? Yes. In that sense, it must be convex, yes, because the feasible region is like an intersection of half spaces. Yeah. And one thing also to note is that if you really want to go for bend optimal, then there are examples that require actually exponential area. Yeah, so it's clear that this is a parameter that you can play with as a trade-off. You can go close to bend optimal in quadratic size grid. If you really want to have bend optimal, then sometimes you need a very large area. Okay. So the second thing talks about the smooth orthogonal drawings and how we can use them. This is just an example of like a traffic network, I think somewhere in Western Austria, where they use that kind of style, using lots of circular arcs in their layout. So it's just an example to show that this layout style is actually used. And what is known here, I already told you that one of the measures to say how good a particular layout is to look at the complexity that you need, or the number of edge segments that you need to draw that graph. And here we define an OC subindex I layout as one that uses orthogonal edges with up to 2 segments per edge. So this would be an OC2 layout, because here actually almost all edges consist of 2 segments. The same graph you can show with smooth complexity 1, so SC index 1 layout, because every edge is now a single circular arc or single edge segment, straight line segment. These have been studied in a series of papers, first for planar graphs, and then more recently they have been adapted for also non-planar graphs where you have some crossings. Okay? And this is a table taken from the paper just to see what is kind of known for these types of graphs. So if you look for the traditional orthogonal style like that one, then it's known that in n by n area, so a quadratic size grid, you can always draw every planar graph and also every non-planar graph with at most 3 bends per edge. Okay. Actually, I think for the planar drawing, there is most of the edges, almost all edges, have just complexity 2, so consist of 2 segments, but some may need 3. And I think the octahedron graph is one where you need 1 edge with 3 bends, if you want to play a little bit with this. So what has been shown in the recent paper last year at Graph Drawing Conference is that if you go now for orthogonal layout with at most one crossing per edge, this is what we call one plane here, then we could show that they are not included in OC3. So there are graphs that need more than 3 edges, but we can always do all of them with 4. So that's kind of tight, and this is also in a quadratic size grid. And you can basically, if you take biconnected outer one planar graphs, so they are outer planar graphs basically, but they might have crossings on edges, then you can save 1 edge segment here in this kind of result. If you go for smooth orthogonal, then I think we don't have to go through all of them, but for example, you could show that in super polynomial area you can do smooth complexity 2, so every edge consists of 2 smooth arcs for all planar graphs of maximum degree 4. If you go to planar graphs of maximum degree 3, you can even do with a single curve per segment, still in super polynomial area. And now maybe the more interesting new result is about graphs with crossings, so going again to one plane graphs. What we could show here is that with smooth complexity 3, so at most 3 segments per edge, you can go into a n by n squared size grid, for all of them. And if it's outer one plane, you've seen that this saves some kind of edge complexity here. The same is true here. So you can always do it with smooth complexity 2, and there are some examples that cannot be done with 1. Okay. So this is a bit of the overview of the state of the art, what is known for smooth orthogonal drawings with up to 1 crossing per edge. Okay, so the next idea for beautifying crossings was this kind of edge casing model. And it's a paper with a nice title, Edges and Switches, Tunnels and Bridges, by Epstein et al. And here the idea is you start with maybe a planar drawing, and then one by one you need edges that you add. And you can think of this as stacking the edges on top of each other. And then if you draw each edge as a black straight line with a white margin, then this is the kind of drawing that you create. So you cut away a little bit a larger piece of the underlying edges on the lower level, and then you have that kind of drawing. And then we need to add one more edge, this one here, which is also above one of the previous edges. So in some sense, you see that you have 3 layers of stacked edges here. Another way of drawing the same graph, pay close attention to what happens here. So what you see here is a different style of edge casing, because it's more like weaving. If you do fabric creation, then you see that this edge overpasses that edge and then goes underneath the next one. A layout like this you cannot achieve by simply getting an order of the edges and inserting them in that order on top of each other. So here you need the weaving model. So this is exactly the 2 models that were studied in their paper, the stacking model and the weaving model, and they have different kind of algorithmic results. Yes, so this is exactly the difference here between stacking and weaving. And some problems that you can try to optimize for these kind of edge-cased drawings, well, there's several of them. For example, you can try to minimize the total number of switches, where a switch is if you follow an edge and it overpasses some edges for a period of time and then goes to an underpass, that would be a switch. Because if it's always on top, there's no switch on that edge, and if it goes top and bottom, top and bottom, top and bottom, then there's many switches. Okay, so you can try to minimize kind of the total switches. And in the stacking model, this is still an open problem. In the weaving model, they can minimize that with a polynomial time algorithm, where here this value k that you see here is basically the number of crossings. So the kind of overpass, underpass that we need to decide. Of course, all of them are at most m squared, but they can be less. Yes?
Similar to one other criteria, make span.
Make span?
Yeah, minimizing the maximum switches.
Yeah, but that's this one, right? Minimize the maximum number of switches. Yeah, so I think that's the one. Yes, to minimize the maximum number of switches per edge, but this is open in both models. So it's an interesting question to study, but this paper doesn't bring any results here. Yeah, the max total switches is kind of in parentheses because from an aesthetic perspective you would not want to maximize number of switches, but maybe if you see this as some kind of idea of weaving some nice patterns, maybe it's actually nice if something goes top and bottom. And the same idea for minimizing total switches also works for maximizing. And then in the second part, they look more at the tunnels, where one tunnel is basically this underpath here, and then there can be criteria like the length of tunnels. And if you imagine that you have two edges that cross at different angles, then for the tunnel length that makes a difference. So here you see some geometry coming in. So if you think of an edge like this, and you always have some kind of distance to the edge, then here the tunnel would be kind of long. Let's maybe color it in red. And if you have 90-degree crossing, then the tunnel is much shorter. Okay. Still with the same kind of distance or using the same kind of casing width here. And if you think about these problems, minimizing the maximum tunnel length or maximizing the minimum tunnel distance, so the distance between any two tunnels on the edge, then you get interesting algorithmic problems that also now depend on the actual embedding of the graph. Yeah? For the stacking model, there are efficient algorithms for doing that, but they are randomized, so they run in expected time. For minimizing the maximum tunnel length, they have a hardness proof in their paper, and the other two problems, they do have efficient algorithms. So if you like these kinds of drawings, then that's a good reference to look at, and it has not been much follow-up work on that part. Yeah?
So they expected them, so why? I mean, that's just kind of...
I don't have the exact algorithm in my head right now, but I just remember that they are randomized algorithms. So I would have to check why exactly. Okay. Yeah. And the final idea is to look at bundled crossings, where we try to group mutual crossings of two disjoint edge sets E1 and E2, such that we can enclose all of those crossings somehow in a pseudo-disk, so we can kind of group them together locally. So they studied in these two papers in 2014 and 16 kind of this bundled crossing number problem. So if you have a graph, you want to know how many bundled crossings do we need for a particular graph. And here we need to partition all the crossings of a given embedded graph, so you have kind of the geometry, you know where the crossings are, but now you can kind of morph the edges in the same homotopy class in some sense to group crossings in these kind of pseudo-disks. And we want to minimize the number of bundled crossings. So what they showed in the paper, kind of not very unexpectedly if it's about crossing numbers, is that minimizing this number of bundled crossings is actually NP hard, no matter whether you have an embedding to start with or you can even choose that. And then what they mostly did is looking at approximation algorithms, for example, using circular layouts, where you have all the vertices on the perimeter of a disk, and the entire graph lives in the inside of the disk, and here you can get some constant factor approximation for these layouts. Okay, so the second part now is about eliminating the crossings. And we will see the Confluent drawing style and this partial edge drawing where we take out some parts of the edges. So Confluent drawings have been introduced almost 15 years ago now by Dickerson and others. And in terms of the definition, we say that a graph is confluent if it admits a planar drawing with special properties, namely that vertices correspond to points, like usual, and edges correspond one-to-one to locally monotone curves. And this is kind of the idea of following a smooth curve without making a sharp turn anywhere. Also called train track layout in, I think, one of the papers. And for example, if you have this sub-drawing in your bigger drawing, it would not mean that these two guys are connected. Of course, the two arcs meet, but in a point that is not 180-degree angle, basically. Yeah, so these would now, from here on, have the same neighborhood because they merge into each other, and from then they are undistinguishable, but they are not adjacent by themselves. Yes, so this is not allowed. And now you can make some easy observations of which kind of graphs do admit confluent drawings. In particular, complete graphs and complete bipartite graphs. So the most crossing complex graphs that you can imagine, they are actually confluent. So you can draw them without any edge crossings. Okay? So this is kind of nice. So the first one, you can see we have a bipartite graph, K2, 3 in this example. Both white vertices are adjacent to all black vertices, and all black vertices vice versa to all white ones. And you can do this with any bipartite graph. And for the complete graph, one way of drawing it is using this kind of roundabout idea. But you can also have a different drawing of K5, that if you don't like this kind of roundabout, you can take two extremal vertices and then connect all the others like that. Right? And here you have also the one-to-one connectivity. So what has been studied is to understand which kind of graphs admit these confluent drawings and which do not. So for example, if you think about a complete bipartite graph and now you take out a single edge, you immediately run into a problem. Right? So it's not hereditary graph class in the sense that when you take away some edges, build a subgraph, that the property would still hold. So cographs, for example, is one graph class that has been studied here. Cographs are defined by starting with single vertices, and then there's two operations that are allowed, namely unifying two cographs into a single graph, so taking the union of the vertices, or taking the complement of a graph. So every non-edge becomes an edge, and every edge becomes a non-edge. So cographs are actually graphs that always admit confluent drawings. And likewise, any complement of tree or cycle allow that, any interval graph allows that, but there are also some graphs that are clearly not confluent. And for example, one thing that they show in their paper is that if you take the hypercube graph, if you go to 3D, it's just your regular cube graph, and you see here an example of how a confluent drawing of that one could look like. And if you go to the 4-dimensional hypercube, it's no longer possible. Yeah, so there's positive and negative examples of confluent graphs, and it's interesting to study or to understand more closely what can be done here. So this is still kind of open to fully understand what are the confluent graphs. And one variation that has been studied a bit later is the so-called strict confluent model. So the edges, it still needs to be a confluent drawing, but every edge now needs to be represented by a unique curve. So what we do not allow is that, I don't know, this vertex and this vertex can be adjacent via two paths. Yeah? So that would be impossible, and it's also not allowed to have any kind of self-loops in the drawing. So if you take out these two structures, then what can we show? Then at least we know that it's NP-complete to test whether the graph has a strict confluent drawing. If nothing is given, but if we have a graph and we try to do this circular layout style that we also have seen before, like a little bit, with a fixed vertex order, and for those working on the mixed linear layout problem, of course a circular layout is nothing else than a two two-stack layout, if you take your line and merge it together. So if the vertex order is fixed, then one can decide in n squared time whether this particular layout has an outer planar strict confluent drawing with that particular ordering. Okay? And here you would see one of those. I mean, you need to decide for yourself whether these graphs are very well readable. But if you compare them with the number of crossings that you see here and how dense they can be, it's maybe not so bad to try to follow a particular track. And in particular, because here we have unique tracks, then it's kind of a little bit easier to see what's connected.
Confluent drawing.
Yes.
Do you know any about the total length of curve?
No.
If it looks
You could try to, I mean, yes, this is just an existential thing, and you could try to minimize somehow the length of this maybe tree-like structure in some kind of minimum confluent spanning tree model or Steiner tree, whatever you like. But no, minimizing edge length has not been studied. What has been studied is, I think, the curve complexity of this model. And I think here you could show that every circular arc going from either junction to junction or vertex to junction can be drawn consisting of two consecutive circular arcs. But of course, then if you pass through many junctions, your connecting path has many junctions. So what would be open here is what happens with these kind of graphs, so outer confluent, if you drop the ordering restriction. Yeah, so that is not well understood. Trying to recognize which graph have strict confluent layouts. So it's kind of a subset of the problem of understanding which graphs have confluent layouts. Because this is more restricted, there's more hope to have progress here. And then also maybe study the total curve complexity that we need. And like we can add edge length. Okay, so the last of those 5 blocks was about cheating in the sense that we just don't draw the crossings. And while this might sound like an easy problem, there's also some algorithms and optimization problems behind it. So if you take a randomly generated graph, say with 20 vertices and 100 edges, and you do you do force-directed layout, so trying to have connected vertices close to each other and disconnected vertices kind of repel each other in some kind of electrical model. You can think of positively and negatively charged particles. Then a layout could look like this. And I mean, we didn't talk about these more practical algorithms this week, but force-directed layout is basically the algorithm that most of the drawing tools have as the default. Yeah, because for many graphs, it produces reasonable layouts, but here you just see, like in a random graph, it's not unexpected that there's no single vertex that has connections to everything, and there's not so many vertices that have degree just 1 or 2. All look very similar. And this particular drawing with just 100 edges has already 413 crossings. So it's quite large. And the idea of partial edge drawings is to maybe take a portion of the edge, say 50%, so the middle half of the edge, and take it out. Then, of course, the vertex positions stay the same, and now you can count crossings of the remaining black parts of the edges. Let me see. Put the number here. So this would only be 23 crossings. And now you need to do like kind of an exercise to see whether you can read adjacencies of vertices better on the left or better on the right. And in order to learn how to read these drawings, this is a particular style where I think exactly 50% of the center is taken out. So if you see an edge stub like this, it's kind of short. It indicates that the neighboring vertex will not be so far away. If you see a long stub like that one, it means that it's kind of far away. And it's symmetric in the sense that on the other side, you see a stub of exactly the same length. Okay, so this one is a long stub pointing in that direction, and it meets another long stub, so you can say that these two vertices are connected. Okay, if you go here, maybe That's strange. Thought it's the same graph. But here there's clearly no edge. So maybe this is actually pointing here. Okay, so yeah, it's not so easy. Okay, I guess this one does not point to that vertex, but to that vertex. Yeah, and you can see that up here you find a long edge, but it's not pointing to the vertex, but slightly at the side. Okay. Yeah, so I think I highlighted two pairs. For example, these two, they are connected by an edge which is passing very closely by their vertex, and if you're not careful, maybe you don't see that this is just going aside. Here you have the two stubs, and they are so long that it's clear that this stub does not connect to that vertex, so the only chance is the other guy. And this is another pair that goes through a very dense region over here. Again, you have two stubs of a length where it's kind of clear that this vertex is not part of that edge. Okay. And you can read the connectivity. So the question is, yeah, is this just like a toy problem, or does it help? There has been done a user study by some more applied colleagues, Bush et al., who looked at how well users can still read connectivity or things like degree of a vertex, depending on what portion of the edge they draw. It's not exactly the same model because they take directed edges and only draw the first k% of the edge. Yeah. So if you see something like this, it means it's a directed edge going basically to that vertex. And then they looked, okay, what happens if you take full edges 100%, 90%, 75, and so on. Let me see, I think I didn't put the results, but what they could show is that somehow this range of 75, 50% could still be read reasonably well. Here you have many crossings, which is kind of confusing, and here these are just too short to make any meaningful connections. Yeah? But it showed that it's really also something that people can understand. So if we look at this from a more theoretical point of view, we define this notion of partial edge drawing, where we have remaining parts of edges, we call them stubs. And from the theoretical model, we want the stubs at a length so that no pair of stubs intersects. So we get rid of all the crossings. The previous example was 23 crossings remaining, so we would have to shorten even further. And then there's different variations of partial edge drawings. They can be symmetric or non-symmetric, and they can be homogeneous or non-homogeneous. Okay? And we see all combinations down here. So the first one is a symmetric homogeneous partial edge drawing, and the 1/4 basically says how long one edge stub is in relation to the full edge length. So a quarter SH pet erases the 50% center part of each edge, and then 25 is on that stub and 25% on the other stub. Yeah, so this is a drawing where you have this nice property that the length of a step tells you in which distance to expect the neighbor, and the symmetry tells you that it's easier to find a match between the pairs. If you forget about the homogeneous constraint, then for every edge you can decide how long you make your stubs. So for example, you can draw some edges long without any gap, and others might be shorter. And now you don't have anymore this nice property that you can kind of estimate the distance. Homogeneous partial edge drawings, but without the symmetry constraint, simply mean that for every edge you delete the same portion of ink, but it's no longer clear that it's always in the middle. Yeah, so you see that maybe, what do we have here? Yes, somewhat one stub is like 50% of the edge, and then there's a gap of 25%, and the second stub has 25%. Something of that style. And if you forget about symmetry and homogeneity completely, you're just interested in, for every edge, finding a pair of stubs of, say, maximum length, so that you have no more crossings. Yeah, of course, for readability, these are best, but maybe in terms of ink, you can do more here. You see that this is kind of very white space, you delete a lot. So there's several results trying to understand what kind of drawings are possible for certain classes of graphs. What can we say about the maximization problem of having as long stubs as possible, etc. So for example, you can show, and this is maybe not unexpected, that for a fixed delta, so having a fixed portion of the stub length, of course not all graphs admit that kind of drawing. There's a counterexample of the complete graph with 164 vertices that has definitely no 1/4 SHPED, so of that type. But of course this bound is not tight. I think we have an example of K17 or something like that that can still be drawn, and we expect that very closely later. It's impossible. But for showing this K164, we use somehow that we can find a subset. No matter where we place the points in the plane, we find a subset in convex position using Erdős-Sikeres kind of ideas. And then for this subset in convex position, this has a certain number of points for which we can then show that we need crossings if we have that kind of stub length. If you take Kn and you want to find out what kind of delta we need so that we can draw it, this depends now on the number of vertices. And what has been shown in, I think, the first paper here, was that if you take the square root of 4n divided by pi, then it's always possible. Yeah, so these kinds of results have been studied. And then more on the algorithmic side, we can look at the max PET or max S-PET problem of maximizing the stub length in either this type of drawing or this type of drawing. Okay, now we can decide for every crossing, basically we have to decide which of the two edges stops early enough so that the crossing disappears. So if you take two plane graphs, so these are graphs drawn in the plane with straight edges and at most 2 crossings per edge. So we start with a geometric embedding and we need to decide how short to draw each edges. Then we can do this in n log n time exactly for 2 plane graphs. But if you go for max SPED, so going for more crossings than just 2 per edge, then it's already NP hard for 3 plane graphs in the SPED setting and for 4 plane graphs in the PED setting, so in this setting. Okay. You can also look at the dual problem of minimizing the amount of edge lengths that you erase. So in terms of the exact solution, they are exactly the same. But in terms of approximation, it's different, whether you minimize the deletion or you maximize the remaining part. So this can be approximated within a factor of 2. And yes, so what's open is, for example, finding a smaller counterexample than this very large complete graph here for the first result, or to look at this kind of gap that is between max PED hardness and tractability. Yeah, so we know for 4 plane graphs it's hard, for 2 plane graphs it's easy, for 3 plane graphs it can be anything. Okay. So much for the first part. So I showed you different styles of how to handle crossings kind of in a layout or geometric sense. In the second part I want to show you a recent result about crossing minimization that I did with a PhD student, doing that in circular layouts. So here the principal idea is that you're given a circular layout of a graph already with a fixed vertex order, so that makes things nicer. And for those liking linear layouts, this is a 1-page book embedding or 1-stack layout, but with many crossings, so it's kind of invalid. The question is, what can we do here? Because the crossings, they make it hard to track the edges if there's too many. Crossing minimization in these circular layouts or 1-page book drawings, this is hard. And one idea that has been proposed in a previous paper is to use the outside of the circular layout as well for some of the edges. So the goal here would be to find a subset of the edges here, colored red, and instead of drawing them in the inside, we draw them in the outside. And now the condition is that the edges in the outside, they have some kind of disadvantage because they make a big detour. If you want to connect like 2 opposite nodes with an outside edge, you have an arc of basically half the perimeter of the disk, whereas the straight line would just be the diameter. So in some sense, they are already harder to track. And then we require that we don't put too many crossings on them. So for example, you can say the outside edges are a planar subset of edges, or they have at most 1 crossing or at most 2 crossings, etc. So the question now is, can we find the best set E prime of red edges to put to the outside so that the number of crossings is minimized? So this is kind of a constrained crossing minimization problem where the hope is it's not hard. Or maybe in some senses you can deal with it. So what happens if we do that idea? So we take the set of red edges. Yes. Yeah, we will see that it's hard in the general case, but if you take a fixed k, say planar or one planar outer edges, then you can do it. In some sense, it's like a max set idea. Yes. Yeah. But we will see exactly. So what we have is we just draw the remaining black edges in the inside and then put the red edges on the outside. Okay, this is the type of drawings that you could get here. Now this is drawn a little bit like the Confluent style. So from this vertex you see 5 edges emanating, yeah? And they share basically their radial segment. And then I highlighted the crossings on the outer edges by these 3 boxes. So what you see is that we took out the red edges. We obtain an almost planar outer part with just 3 crossings, and no 2 of them are on the same edge. So this would be a one plane red edge set in that sense. So the first one has 45 crossings. This one has 14 crossings in the interior and just 3 on the outside. Yeah, so if you just count crossings, maybe this is much nicer to have, but of course the outer edges are somewhat special and more difficult to read. So what is known about this? It was suggested to use the kind of two-sided circular layout already in 2006. And they also presented a 3-phase process of first heuristically ordering the vertices on your circle in some nice sense, then computing external edges, and in their work they were interested only in planar external edge sets. Yeah, so this is a valid stack page in some sense. And then in their final step they did some edge bundling to reduce the complexity here a little bit. But that's just heuristic and visual techniques. Oh yes, and computing this optimal set of external edges, in their paper they do in a cubic time algorithm. You can also use an independent set algorithm by Valiente that runs in quadratic time in terms of the number of edges of the graph. Yeah, so that would be an alternative. Okay, so what do we mean exactly by our problem? We will use a lot the circle graph that we get from this particular layout. And this is an intersection graph using the chords of the circular layout as the vertices. Okay? So we have a number of edges here, and some of them intersect, others do not intersect. Every edge becomes a vertex in the circle graph, marked in red here. And we connect any 2 vertices in the circle graph if their corresponding chords intersect. Okay? So these 2 blue chords do intersect, so we have that red edge in the circle graph. Is it clear? Definition? Okay. So in total, I think this would be the chord intersection graph of that particular circular layout. And 2 vertices are connected if and only if the chords intersect. So now we need to kind of try to optimize which edge set we pick from the circle graph to put it on the outside. And we define a slightly more generic problem that we call K bounded degree maximum weight independent set. That's the abbreviation here. And it means that if you're given a weighted graph G and some integer K, we want to find a subset of the vertices so that the induced subgraph on this subset of vertices satisfies the degree constraint, so has at most degree K. And we want to maximize a sum, so optimizing over all possible sets with that property, so that the sum of the vertex weights is large and the sum of the edge weights is kind of small. We will see how that helps us to do the crossing idea. So if we set the weights of our problem to for the vertices to the degree, this will be the vertex weight. So if we take one of the edges out from the circular layout, The degree tells us in the circle graph how many edge crossings we remove. Okay? So if we maximize that, we try to remove as many edge crossings as possible. And then for edge weights in the induced subgraph, we can either set the weight of 1 or the weight of 2. What does that mean? So if we take a pair of edges that cross in the interior and put both of them to the exterior, they will still cross in the outside. Okay? And we can either say crossings in the outside is also something that we want to have small. Then we set the weight to 1. Or we don't care about the crossings on the outside. We know there's at most 1 per edge. Then we can subtract 2. So this is kind of slightly different model, but the generic problem covers both of that. And then the weight W that we get here is kind of the number of saved crossings, depending on one of the two models. Yeah, so we want to find this kind of weighted independent set in the circle graph. So what I explained in words now, if it hasn't been clear, maybe in the example it becomes a bit clearer. So if this is your input graph, we take one of the edges and we see how many crossings that one has with other edges. 1, 2, 3, 4, 5, 6, 7, 8. So this is a degree 8 node in the circle graph. And if we take that one to be on the outside, we immediately save 8 crossings. Okay? And currently, when we have a single vertex in V prime, then this would also be the target value. So now we can take, and we draw it on the outside. We take a second edge, like that one here, and we imagine putting that one also to the exterior. So this one has 2 crossings in the initial graph, but one of them with the edge that has already been removed. And the other one, yeah, this is the green one, and the black one is a crossing that we really save. So it's a degree 2 vertex in the circle graph, but if we put it on the outside, it now depends on how you count crossings. So we save 8 plus 2, but minus 1 because that one is still now on the, let me draw it, it's still here. Okay. Now depending on your model, you either count that crossing or not. Okay. So that's the model, and first we look at the complexity of that problem if k is somewhat free parameter. We show that this optimization problem is NP-hard on circle graphs, even if all the vertex weights are 1 and all edge weights are 0. So we only do the vertex weight maximization problem. And the reduction uses the dominating set problem on circle graphs. Maybe I can quickly sketch the idea. We have like 10 minutes, 12 minutes, or... Okay, so first of all, what is known from Klein 93 is that if you're given a graph G, we want to find a dominating set. So this is a subset of vertices with minimum cardinality, so that every vertex that is not in the dominating set is at least a neighbor of a node in the dominating set. Yeah? And we know from Klein that this problem is NP-hard on circle graphs. Okay? So we can use the circle graph idea, or use the circle graph as the input here and then do our reduction with the same circle graph. That's kind of makes the reduction very easy. So the idea is that we want to set the number k to be the maximum degree of G. In this particular example, maximum degree is 3 on that edge, but in general it's some other number. And then what we want to make sure is that in our kind of instance that we get in the reduction, every vertex has now degree k plus 1. Yeah, so we add more chords in some sense so that we get a graph that has all vertex degrees the same. So what you can do is you can simply attach kind of leaves to that circle graph so that we make all the vertex degrees to be 4 in this example. This is an edge that had degree 1, so if we add 3 of the red edges as leaves of the graph, we have a degree 4 vertex of the interior. And you do that for all of them. This can easily be done in a circle graph fashion. Yeah, so the graph that we construct here is still a circle graph. And then we set the vertex weights to be 1 for the vertices and 0 for the edges in our reduction. And now, to show that this reduction actually works, we take our circle graph. We have G prime to be the copy of the graph, but additionally having some leaves so that all the internal vertices have the same degree. And then we need to show that if we have a minimum dominating set, it corresponds to a solution to our K, BDM, whatever problem, and vice versa. So if we take a minimum dominating set VD of the initial graph G, then we can look at the complement of the vertices. So VS is the set of all vertices without this dominating set. And what we know is that the graph that is induced by that set has maximum degree K. Why is that? Well, it's a minimum dominating set. So for every internal vertex, there must be either that vertex is in the set, or if it's not in the set, then it must have at least one neighbor that is in the set. So in this induced graph, it can have certainly no degree K plus 1. Otherwise, it would be invalid. So we know that this induced subgraph here has maximum degree K. And now for one of those vertices in V prime, we know that the complement set Vs contains all the leaves. Because in a minimum dominating set, it would never make sense to have a leaf in the dominating set. Yeah? Because then you could also take the interior node, and that would be even better. So Vs certainly contains all the leaves, and if Vd was the smallest dominating set, then we know that the complement here, Vs, is actually the largest set satisfying the property that the maximum degree is K. And because we set our vertex weight to be 1, our goal is to make Vs as large as possible. Yeah, so that's one half of the reduction, and the other one is taking a solution to our vertex degree constraint weighted independent set problem, and then show that this corresponds to a minimum dominating set. So again, what we can assume is that all the leaves are actually included in our solution to that problem. If you assume there would be one leaf that is not in the problem, because we know the maximum degree is K, every internal vertex has one neighbor that is not in the set. And it could be a leaf. But if there is a leaf in the set, and this is maximum, we know that all the other neighbors are in the set. And in particular, there must be an internal neighbor that is in the set. And now we can just swap them. Okay? So this has degree K. We swap it with a non-leaf. We get a solution of exactly the same weight. So that would be without loss of generality. We take one of those solutions. And now we can play the same argument. We take the complement. We know all the leaves are in Vs. So when we take the complement, what we get is actually a subset of vertices of the original graph, because no leaf is in the complement. And then this must be a dominating set, because the induced graph on Vs has maximum degree K. Yeah, so every vertex that is in V is either in Vd or it has a neighbor in Vd. Yeah? And because we maximize the cardinality of Vs, we know that Vd must be the minimum solution. If there would exist a smaller one, we could have found a better solution for Vs. Yeah, so that's kind of a sketch of the correctness idea here. Okay, so now let's quickly see what we can do in an algorithmic sense here. And what we could show is that we can solve this problem in running time where the exponent is basically linear in K. Yeah, so for small k, you get a polynomial time algorithm, but of course if k grows, then the running time also becomes exponential. So this is also called an XP time algorithm if you have running times of the order n to the k for some parameter k. And the idea of solving this is to use dynamic programming. So you know a lot about dynamic programming from the previous lectures. We will also use that here. But one step that we do before that is to go from our circle graph to an interval representation of that graph. And this you get by taking your circle representation and now projecting all the edges from, say, the north pole of that circle to some line that is below the circle. So if you do that projection, you project every vertex onto a real number on your real line, on the x-axis, and every chord of the circle becomes an interval. And now what happens with the intersections here? So if you had two intersecting edges like that one and that one, this becomes this interval and the other one becomes that interval. Okay, because they intersect, it's clear that also the intervals need to intersect, but they also do this in a proper sense. Yeah, so one interval contains the endpoint of the other. And you might also have, in an interval graph sense, edges between nested intervals. Yeah, so this one corresponds to that edge, which does not intersect, of course, this long edge here, which is here. But if you go for overlap graphs, you don't care about nested intervals. You only care about properly intersecting ones. Yeah, and Gavril also already in the 70s showed that circle graphs are exactly the same as these overlap graphs. Right. So we use this interval representation for the algorithms, and there's basically three cases that we can look at. The first case is finding a planar outer set of edges, and here we can use the independent set algorithm of Valiente that works for that. And that's also kind of inspiring the ideas for the other cases. For k is 1, we adapt that algorithm. If k is more than 1, you need different ideas, and I will show you why this is slightly more complicated. So in the case k is 1, what you can do is you sort the intervals by length, and you start processing the shortest ones, and then when you go to larger instances, you have already computed the shorter solutions. Yes, so for every interval you have two options. We could not take interval I, and then we need to compute the best solution on this yellow region, but this will not be part of it. Or we do take I, and because we have k is 0, we do not allow any crossings. So all the other intervals that we can choose for our solution must be properly nested in that range, or they are right of it. Okay, now we can split into two independent sub-instances, and then the dynamic programming recursion basically puts that together. So what changes if we go, and the running time is what we have seen already. If you go to k is 1, there's a little bit more cases, but we can still use a somewhat similar idea. So this is what we've seen before. We can take an interval not at all. We can take a single interval and recurse. Or we can look at a pair of intervals that intersect mutually. So this would be the degree 1 that we do allow. But once we have that, it's clear that no other interval can cross that line or that line, because then one of those edges would have degree 2. Okay, so this third case basically splits one instance into 4 independent sub-instances. So the recursion gets a little bit more complicated because we have a larger case distinction here, but the idea still transfers. Yes, and the running time grows a little bit, where this factor gamma, I think, is the number of crossings in the circle graph, and this will be number of edges to the 4th. Okay. And finally, if you have k larger than 1, the difficulty arises that now we can have arbitrary long paths or even cycles in this intersection graph. Yeah, so the natural extension of the case, going from a pair of intersecting crossings now to something that has at most 2 crossings, means that immediately you get very long structures spanning your entire graph. And instead what you can do is kind of introduce so-called capacity vectors that kind of store the information of how many crossings one particular interval already has used and how many are remaining. Yeah? So in this example we have some capacities written on the endpoints of the edges. So this one still can do 1 crossing. This has already used all crossings, likewise here. So if we set k equal to 2, at most 2 crossings per interval, then we cannot, for example, use the green interval because blue has no more free crossings. If you set k to 3, then these capacities are slightly higher, and for example now you could pick the green one, decrease that to 1, decrease that to 0, and so on. That's the main idea. So we look at how many possibilities we have for these capacity vectors and then try to optimize over all possible choices for legal capacity vectors in some sense. Okay, I don't go into the detail, but the running time now increases to 2k plus 2, and this gives us the result. We did implementation for cases k equals 0 and k equals 1. What you can see is that this is the number or the percentage of saved crossings. The red box is k is 0, so no crossings on the outside. And green and blue are crossings on the outside, but the 2 options of counting external crossings or not. In terms of saved crossings, that doesn't make a big difference, but you gain like 5 to 10% if you do that. And in terms of running time, of course, the independent set algorithm by Valiente is faster, so the red box is maybe a factor of 10 to 100 faster than the other algorithms, but you can still run that in reasonable time if your instances are not too large. Just to show you a possible output, so if this would be one of our input graphs, and you have k equals to 0, then this would be the resulting layout. If you allow one crossing per outer edge, then this would be your layout. And in terms of crossings, you start with 125. This has around 50 crossings, and here you save up and have only 30 remaining. Okay, so to conclude, we have seen that this problem is NP hard, even on circle graphs, but we have an XP time algorithm solving that for small k, and even did like a small implementation for the easy cases of 0 and 1. Yeah, for doing the capacity vector stuff, you need a lot of machinery, so we're not very hopeful that this gives an efficient implementation. In terms of future work, you can try to improve this algorithm idea and maybe use ideas like tree decomposition of the graph, whether that helps. It would also be interesting to maybe have some edge bundling in the interior of the circle, to have bundled crossings idea, basically, or extend some of these ideas to other layout styles. This is the pre-final slide, just to raise your interest for topics related to non-planar graphs. Yeah? So studying slightly non-planar graphs, they are sometimes called beyond planar graphs, is a very recent topic in graph drawing that has been studied from mostly a theoretical point of view. For example, you can study k-planar graphs that have drawings with at most k crossings per edge. Especially the focus is on one-planar graphs, with at most one crossing per edge. And interestingly, recognizing planar graphs you can do in polytime. Recognizing one-planar graphs is NP-hard. There's also notions like gap planar graphs, which are somewhat related to the edge casing model that we've seen, where you try to minimize the number of gaps that you have. Quasi-planar graphs, these are graphs where no k mutually, so no subset of k edges pairwise crosses. So you exclude somewhat triangles or k-fours and so on. There's pan-planar graphs. There's graphs where the angle of crossings needs to be 90 degrees. There's almost planar graphs that have maybe a single or two edges with crossings, but many possibly. And you can study all kinds of topics on those. If you want to learn more, then hopefully this year there will be a handbook edited by Sok-Hee Hong on all topics of beyond planar graphs. But until then, there's a very nice annotated bibliography on one-planarity. Okay. Again, this is the further reading list, but we don't need to go through it. And with that, I would like to thank you for attending for the 5 lectures here, and for hosting this event, for organizing it. It was all very perfectly organized. Felt very welcome here, and I thank you all for participating.
It was the last lecture of Dr. Martin Nöllenburg, and if you have any questions about the lecture, maybe 1 or 2.
How many? 1.
Are there any lower bounds on the time complexity of computing problems for PDK?
The last one that I showed lower bounds, no, we did not show any lower bounds. So if you like lower bounds, yeah, maybe.